Okay, welcome to the track on Achieving Earth Independence. My name is Doug Plata. I'm an urgent care physician. And we are going to be discussing the current thinking about how an initial base, such as on the moon, can become completely Earth independent. And this track starts the conversation. And I mentioned here that we have milestone number 31 of the National Space Society, which describes about how space settlement can ensure the long-term survival of the human species. So now let me give an overview of this presentation that I'm doing, and I'm going to address exactly what is Earth independence. And there's different types, different ways of looking at it as different types of Earth independence. And then, okay, what are some of the reasons to seek this? And what are the elements of Earth independence? What is it composed of? What things do you need to master to become Earth independent? And can it actually be measured? Can we put a metric on it? How far can we go? Can we actually achieve complete Earth independence? And then finally, just the concept of sufficient supply. Okay? So, what is Earth independence? Earth independence is ISRU, in situ resource utilization, and recycling. Let's not forget recycling. It's very important. And other means of decreasing or eventually eliminating the need to supply deliveries from Earth. So you can probably guess what some of the major components are. Certainly, if you're going to survive long term and not have to ship all of your air that you're going to breathe or your food, well, life support, food, you have to produce the stuff that makes up the colony. So you need to master chemicals. You got to produce parts. So you got to extract the metals from local resources and make parts. But boy, then it gets sort of to the hard part, doesn't it? Actually producing power supply. Fortunately, we're doing pretty good on that point. And then the big one, electronics. Can we actually produce electronics off Earth? If you think about everything it takes to make a CPU, that's a tough one. And then finally, of course, if you are looking at long-term survival, you can't just have a handful of people because you'll have genetic collapse. So what about the minimum viable population? Okay, two types of Earth independence. And what I'd like to say is there's different ways of reasoning. There's like reasoning from analogies, which is fun to do. And then there's sort of reasoning from first principles or more specifically the relevant factors. And so as we think about the Earth independence, we can think of a couple of things. We can think about general independence. And normally, this is how space advocates think of Earth independence. It's the idea that we're going to have the Starship deliver passengers to Mars, and after you reach maybe 1 million, plus or minus 1 million, then you reproduce a civilization, and only civilizations are able to achieve to self-sufficiency and self-sustaining. So that's sort of the general idea that most space advocates think about Earth independence is it's just the natural outcome of large-scale settlement. You don't really think about trying to become Earth independent, it just happens, okay? But then the other approach is more looking at the relevant factors and say, okay, what exactly does it take to become Earth independent? And you start going through and saying, okay, how do we achieve this, that, and the other? And what's the minimum number of people and what's the equipment that you need to achieve that? So it's what we call a survival colony, a colony that's specifically designed to be able to achieve Earth independence as soon as possible. So if you reason by analogy, you will say, okay, the only way we can achieve Earth independence is reproduce what we've got on Earth, you know? How do you produce all the things around us? Well, you got to have a supply chain and shipping and intermodal sorts of things, and we need everybody doing specialization. Okay, that's one way of looking at it. The other way is almost like your Maslow's hierarchy of needs, but sort of a technical version of that, and say, okay, exactly what are the elements that are necessary, and then how can we meet those needs? So what are the elements of Earth independence? Well, there are, in fact, I'm going to put this up here. So there are the things that if you don't have them, It's going to kill you in minutes to hours. Obviously, if you have no air pressure, yeah, you got to supply that, otherwise you're not going to survive. You got to breathe. That's the next thing that's going to kill you. If you don't have temperature, you're going to freeze to death or boil to death. You got to have power. If you have a base without power, how long are you going to survive for? You know, and the electronics. If you don't have the control systems, whatnot, you're also going to die pretty quickly. So we can look at it this way. But then there's the intermediate. If you don't have these things, days to months, you're going to die. Okay, you could die of thirst. So obviously, you need to go ahead and produce water, drinkable water. You need to grow your own food. You know, a few weeks you're going to be dead if you don't grow food. You need to reproduce your equipment, and different equipment is sort of more urgent than others. Some equipment is pretty important, you know, like recycling equipment. Radiation protection, the next solar particle event will kill you, and that's going to happen every, I don't know, 4 or 5 years, something like that, or months, something like that. Sanitation, you better, obviously you better take that into account as well, okay? And then there's this category of things that is going to take sort of a long period of time, and that is, okay, you start with a habitat that you ship there, but if you are going to survive long term, you need to replace the habitat. So you need to look at how can you do that, but how soon do you need to replace your habitat, you know? We've got stuff on the International Space Station that's lasting for quite a number of years, but eventually you got to produce your own habitats. Isolation, I'll sort of get into this in the last presentation, that is, to be Earth independent, if you always got connection to the Earth, we got people coming in and whatnot, if any sort of infectious sort of thing happens on Earth, then it could take you down. So there is a need to be able to have a quarantine sort of policy or approach. Sufficient gravity, this is the big question mark. How much artificial gravity, like centrifuge, do you need? Can we get away with the natural 1/6 or 3/8 gravity, or do we need to do centrifuge? And even if you do centrifuge, is that sufficient? There's all of these questions that we probably are not going to know until we go there. And then information, something that we oftentimes don't think about because it's not a material thing, but you need to know how to produce the equipment. You need to know, as the settlement expands, what more things do you need to know? So there's this whole information thing. Genetic diversity, pretty straightforward. And the one that's not thought about, and that is, well, if you have an independent colony, eventually you're going to use up your local resources. So in order to survive long term, you also need to translocate. And that could be a matter of years before you need to do that. Okay? So what are some of the reasons or the rationales for Earth independence? If you can produce stuff and become more Earth independent, you can reduce your shipping cost, okay? Something that's not thought of frequently is you can increase the security of your supplies. If you're on the moon or on Mars, and if you used up your last, I don't know, filter or whatever, and lo and behold, that breaks down, if you can reproduce and keep your stockpiles maintained, that provides a level of safety. And then, of course, the big reasons for Earth independence is survival of the human species, and if you're really grand, what about surviving part or all of the known biosphere? Okay, so let's sort of go through some of these things. So if you're able to produce materials off Earth, it can do one of two things. It either reduces your launch cost, but if you're having to maintain the rocket system, you may not be saving a whole lot, okay, unless it's shared with other launches. But also, if you are able to produce a lot of your own stuff, then what it means is that you can actually grow the base faster. You keep the launch rate the same, the supply rate the same, but you are able to launch more people and electronics rather than all of these parts that you're now making there. Let's talk about safety of supplies. So in a couple of situations, this would be important. If you do have if Earth is doing well and you can get supplies, but you're running out of something, sort of a temporary interruption, some rocket explode, there has to be an investigation and find out what went wrong and make the fixes. If you can be producing your own stuff, then that will help keep you going. So there's that advantage. But also, if you, just didn't do your logistics calculations well and you accidentally run out of something, if you can see that those parts are running down, you could go ahead and produce them and maintain that safe supply. What about ensuring survival? Well, this is where, we're not going to get into all the scenarios, but there's many about how Earth you could be disconnected to Earth because something really bad happened on Earth. The obvious thing that everybody thinks about is a big asteroid that wiped out humanity, okay? Statistically, that is so incredibly low, I hardly even think about it. But there are way more probable causes, and I would say self-replicating technology, which we are going to experience before this end of this century. I would say the people who look in this area, they rate those much higher probability. And then, as I mentioned, obviously a long-term goal for space settlement is survival of the human species. And also there's some interesting work at San Diego Zoo. They have a frozen zoo that they're doing, and I've spoken with someone, one of the guys who heads that up. Wasn't able to present at this conference, but there's some interesting ideas about how we could establish a frozen zoo on the moon. I'll mention that in the last presentation. Reasons for Earth independence, this is quite interesting. Like 3 different reasons. If you're trying to reduce costs, any level of Earth independence, if you are producing 50% of your mass, so you don't have to ship that, it's going to save you up to 50% of the cost, okay? Same thing with securing supplies. If you have partial production, that's good, okay? But ensuring survival, it doesn't really help unless you really have achieved 100%. So these are sort of fundamentally different. All right. Can Earth independence be measured? I think the answer is yes. We could talk about percent mass independence as an indicator or measurement of Earth independence. So it's the amount of mass that you no longer has to depart from LEO to the base, such as the moon. And if you reduce it by 50% of the mass, then you're 50% Earth independent. You can look at it that way. So let's say if you have you have to do all your launching and you're producing nothing, well, you're 0% Earth independent, okay? But if you can do some of these things, RSRU, recycling, extending crew stays so you don't have to keep rotating crew, sufficient supply, then what happens is you can become increasingly Earth independent, and by mass you can actually just calculate it, okay? So let's think about this for a moment. These are not real numbers. These are sort of the best guess that we have right now of what's the mass that needs to depart from LEO, okay? So propellant, descent propellant, ascent propellant, water, consumables, food in there, etc. Going down the list. You can quibble with these, and I welcome if your thoughts are, what needs to be changed there. It'd be great if somebody could do a formal study of nailing down those numbers. But what I would like to suggest is that if you can, whether on the moon or Mars, if you can go ahead and extract water, and we know where it is, both on the moon and Mars, and then the organics with it, and with the water especially start producing propellant, and also if you can extract and utilize metals, then what effect on that previous list would just those things have? Okay, if you go through the list, there's certain things that fairly early on you might be able to go ahead and produce. And if you add it up, something about 85%, if you can go ahead and really make your parts out of metals and things like that, okay? The point being is high levels of Earth independence by mass might be achieved relatively early. And I mean like within a few years, or maybe even before crew arrives. There's ideas about how the nickel iron can be extracted from the regolith and have large quantities of things like sheet metal and parts and et cetera, even before crew arrives. So it could be relatively early that we might achieve a high level of mass independence. And this is why I personally believe going to where there are resources is very important. Going to free space you got to ship everything. If you can just send the spare parts to keep operations going, you can magnify what you're able to send and hence produce. Okay, let's talk about recycling. Let's see, how am I doing on time? Okay, yeah, I got about 8 minutes. 3 minutes. Okay, so recycling. Here's an equation, simple equation, and that is, if you recycle something, how much is it equivalent in terms of the mass that you ship? The recycling rate for water on the ISS is about 93%. Okay, so if you run it through, that's the equivalent. If they ship 1 liter and recycle it, it's the equivalent of shipping 14.3 liters without recycling. So recycling can be as powerful as dramatically reducing launch cost, which is what we all focus on. Okay, so there's certain things that we need to not overlook or take for granted. How far can we take Earth independence? So we have an idea of all the things that we need and the sources and the processes that would need to be done in order to achieve increasing levels of Earth independence. Using the moon as an example, we know with a high degree of certainty, I think, especially based on the L-cross results, where the ice is, and if we use excavation, we can get water, and through electrolysis and other processes, we can go ahead and produce propellant, water for sanitation, drinking, and water for plants, okay? Also in the ice, through distillation, we can get organics, and then we'll have a presentation about chemistry, and then what we can do with those to make food as well as parts, like plastic parts. And then special rocks creep, potassium, phosphorus, and rare earth elements. Those can provide the pK and the NPK that plant fertilizer is composed of, and micronutrients can come from the soil. And then the regolith, that's the term for dirt on the moon or Mars. Through extraction, separating out metals and silicon. With the metals, we can go ahead and, through machining and metallurgy and machining, go ahead and produce the parts. And then, as I said, we're fairly advanced in terms of laboratory demonstration of how we can go from regolith simulant all the way to solar cells, with the electronics being the biggest challenge, okay? And we'll get into that in a later presentation. Let me mention a concept of sufficient supply. So imagine you can ship a 1-ton box, a 1 by 1 by 1 meter box, okay? And in that box is filled your latest, greatest AMD CPUs, all right? How long would those electronics last? Typically, we throw away computers because they're obsolete, not because the chips burnt out or something like that. A small amount of electronics could last a long period of time. So here's the idea, and that is, the general concept of becoming self-sustaining and hence Earth independence is establish a base, and then what happens is over time, you supply the base, and the base starts producing stuff until you get to a point where it's producing everything that it needs, and you've achieved Earth independence, okay? But with a sufficient supply, it sort of works a little different. You go ahead and ship stuff to the base, including oversupplying the hard-to-produce things, such as electronics, and what happens is at a certain point, you don't need to ship anything more. What you're doing is you're buying the base time in which it doesn't even need to be supplied, but it's got time until the supplies run out, the stockpiles run out, to implement protocols to produce good enough replacements. Like instead of the latest, greatest AMD chips, it's an 8086 level chip, which has a processing speed of what the computer system on the Apollo lander has, okay? So maybe that's good enough. So at what point do you become Earth independent? You actually be at the point in which you have oversupplied, you've achieved Earth independence, which means you don't need to supply the base anymore because it's going to have enough time to produce the good enough hardware to where again, you don't need to be supplying. Okay, how soon could a base become completely Earth independent? And what I would say is we don't, it's not really clear at this point, frankly. That we're starting the conversation, and we seek to open up conversation about this point to be able to get your input. What we need to do is we need to actually say what is a complete base and actually go through and say what are the items, what are those items composed of, and how do we make each of those parts of the parts. But the cool thing is we can think in terms of how fast do we need to reproduce. We could look at it from a generation doubling time, which is maybe about 20 years. And so it's not like we have to produce a lot of stuff. We need to produce enough stuff so that when, with natural population growth, we're able to keep up with those needs. And then ultimately we need to do a full-time equivalent calculation to actually find out what is the minimum size of base people in the base that we need. Okay, so conclusions, Earth independence is the degree to which a base or a colony doesn't need to be supplied by the Earth, 50%, 100%. There are advantages of reducing cost and survival. Percent mass independence is a useful measure of Earth independence. The ISRU areas are largely known, and there are ideas that you will hear about what we can do. And a high degree of Earth independence may be possible fairly early on, especially when it comes to propellant. Complete Earth independence might be possible early, or it might not. That's what we're trying to figure out here. And sufficient supply can result in an earlier complete independence. So with that, I want to thank you, and we've got a few moments for questions. I can take probably 2 questions. You got your hand up first.
Yeah, at what point would that production allow you to be a net provider to other consumers? In other words, if you see what I'm getting at?
Yeah. Okay, so I'm going to answer it this way, and that is a lot of space advocates believe that in order to achieve self-sustaining, you need to be economically profitable, okay? What we're presenting here is that there's different ways of being self-sufficient. One is technical and one is economic. What we're talking about, there are tribes that are not trading, but they are technically independent. They self-sustain. There's different types of colonies. There's the survival, and then there's the general. The general one, I think, is connected to the market. They supply stuff. There's more to that conversation, but.
What would you say is the minimum feasible population of a survival self-sustaining colony? I'm thinking both from the point of view of genetic diversity with whatever modern genetic advances we can bring to bear, but also the number of people you need to do the things that need to be done to produce all of those things, maintain the machinery and so forth.
Yeah, so genetics, we're going to discuss that in the last presentation, but very quickly, the experience based on Polynesia, it's relatively small numbers of people. Frozen embryos, they last for more than 30 years without reduction in terms of the viability. So you don't need a very large living group of people as long as they have got their container of frozen embryos with wide, unrelated, not familiar, related like the Polynesians were. But in terms of the production, that's the big production of parts. That's a big question, frankly. It's anything from relatively few, like 1.6 full-time equivalents. It's probably not 1.6, but it goes all the way to like 1 million because of the whole supply chain issue. Can you actually produce the particular materials that need fluorine and stuff like that? So I can't give you an answer, and I apologize. Okay. Unfortunately, that's it. I did want to mention one more thing. Could you give me that one? What we're gonna do throughout this track, and the presenters don't know this yet, but we're going to get a little Sharpie, and as we start going through the different things that are needed to achieve Earth independence, we'll go ahead and check off, and by the end you'll see that they're all checked off. Okay? All right, thank you. And let me go ahead and introduce. Yeah. introduce the next presenter. Okay, I would like to introduce Phil Metzger. He's our next presenter. He is from the University of Central Florida, the Florida Space Institute, and he's a planetary scientist and has done research and technology development for Moon, Mars, and asteroids. In 2014, he retired from Kennedy Space Center with NASA. He's on the Space Shuttle launch team and later with the ISS program. He co-founded, I think this is pretty important for this track, he co-founded the KSC Swamp Works, which is a rapid innovation lab developing technologies to work with the resources in space. And he participated in lunar, Martian, and asteroid mission architectures and worked with NASA on its road mapping team. And he has a number of awards, which you can read in the bio. And he's going to be presenting about what are the resources and also what about metallurgy. So I'd like to thank you for presenting.
Okay, thank you, Doug, and thank you all for being here today. So I'm a planetary scientist, and I'd be glad to talk about the resources that are available. I'm focusing on the moon in this talk, and going to talk a little bit also about where do we get metal on the moon, asteroid or meteoroid impacts, metal from native lunar mineral deposits, from the generic regolith that's all over the moon, and then what can we do with that metal? Okay, resources on the moon. The big picture, the moon has a lot of sunlight, so there's energy. It's got real estate. That's one of the biggest resources that we have on the moon. Real estate that doesn't compete with the ecosphere of Earth, so we can have industry on the moon. Vacuum, in a Zen sort of way, the vacuum of space, the absence of pressure, is a crucial resource because we need vacuum for a lot of industrial processes like vacuum distillation. Gravity. The moon has gravity. It doesn't have too much gravity, so it's easy to launch things off the moon. And it's outside of Earth's gravity well, largely. But it has enough gravity so that we can benefit in certain industrial processes. So that's an advantage over asteroids. The moon has a lot of regolith. The material resources are largely in the regolith and in the volatiles that have been sequestered in the regolith. And then there's recycling, which I'm not going to talk about. Okay, so let's focus on the regolith. To understand the regolith, let's look briefly at its formation. 2 steps. Step number 1, the magma ocean. The moon was molten. As it cooled, things began crystallizing. The things that crystallized early typically were dense things that sank toward the core. Later, things crystallized that were lighter than the magma, and they floated to the top. And so the calcium and aluminum type minerals formed the crust. The mafic iron-bearing minerals and the titanium sank. The titanium, the ilmenite, sank down to the core. But it was a very complex process with convection. The titanium was radioactive and it heated, and so it caused things to inflate to become lower density, and so convection started. And so as a result, on the surface of the moon, we see the result of this convection. We see places where the mafic minerals and the titanium bubbled to the surface and formed the mare patches. That's where we find the more iron-bearing minerals, the basalts, and the highlands are the calcium and aluminum crustal material. Looking in more detail, you can see composition variations across the surface of the moon, and even within the mare. Some of the mare have titanium and others don't. And the reason why is because the titanium sank to the core of the moon, but then it came up in this complex processes in the lunar magma ocean, and so some of the mare were enriched with titanium. Also, the creep elements, the potassium, rare earth elements, and phosphorus, they didn't really fit into any of the crystallization that occurred, so they were the leftover materials. But they were convected up in some parts of the moon, but not all the mare. So there is a region on the moon we call the creepy terrain. That also correlates to the uranium, thorium, and potassium. So it's not the same everywhere on the moon. Physically, the lunar regolith looks pretty similar. The micrometeor bombardment process is